Now we're going to talk about some of the properties of functions, some of the properties of the graphs of functions. Let's start with the interval of increase, which is the interval within a function's domain where the y values of the functions increase moving from left to right. Examples of intervals of increase include these two functions right here. Notice as we move to the right, these functions go up. Interval of increase. An interval of decrease, similarly, is an interval within a function's domain where the y values decrease moving from left to right. And so we have a couple of examples of an interval of decrease. An odd function is any function that has rotational symmetry about the origin. This means that if we rotate 180 degrees around the origin, we will still have exactly the same function. So, for instance, look at this curve right here. This is the curve y equals x cubed. Now, if we look at the red portion that I've highlighted in red, if we were to rotate that 180 degrees about the origin, we would exactly fall upon the bottom portion of the curve. And if we were then to take that bottom portion of the curve, which I've shown in green, and rotate it 180 degrees about the origin, it would exactly fall upon the top portion of the curve. In other words, that 180 degree rotation would end up meaning it fell back upon itself. This is called rotational symmetry about the origin. And it is a property of odd functions with rotational symmetry about the origin, that for all values of x in the domain, f at negative x is equal to negative f of x. Well, if there's an odd function, maybe there's an even function. And an even function is any function that is symmetric about the y-axis. This means that if we reflect the left side of the function in the y-axis, we'll end up with the right side of the function, and if we reflect the right side of the function in the y-axis, we'll end up with the left side of the function. So let's look at this curve here. We're familiar with it. It's y equals x squared. Well, if I take that red part and I reflect it in the y-axis, I exactly get this part on the left. And if I take that part on the left, which I've now made green, and reflect it in the y-axis, I exactly get the part on the right. And it is a property of even functions that for all values of x in the domain, f at negative x equals f at x. Now, not every function is either even or odd. The vast majority of functions are neither. But many of our parent functions are either even or odd, although some of them are neither as well. Now, a continuous function is any function that does not contain any holes or breaks over its entire domain. We will discuss a more technical definition in calculus, but for now, it's almost like you can graph it without lifting your pencil off the page. A discontinuity is a break in the graph of a function. Frequent examples include holes, which are also called points of discontinuity, vertical asymptotes, or jump discontinuities. These are discontinuities. Now, another thing we talk about in this course a lot are end behaviors. The end behaviors of a function refer to the behavior of the function as x goes to negative infinity and the behavior of the function as x goes to infinity. Negative infinity is the far left and infinity is the far right. When stating the end behaviors of a function, we state two such behaviors. We state the value to which y is headed as x goes to negative infinity, far left, and the value to which y is headed as x goes to positive infinity, far right. There are rare exceptions when we cannot state two end behaviors for a given function, but the general rule is that we always state two. Since x can never reach negative infinity or infinity, it is possible that y will never reach the value that is assigned for the particular end behavior. That's an introduction to the concept of limits, which will be discussed at great lengths in calculus. And now, what are parent functions? Well, as you might recall from grade 11, certain functions that one should know in order to be able to properly graph curves are called parent functions, and we're going to go through some of those examples in a later slideshow. So let's look at this question. We want to determine the intervals of increase and decrease for the function on the right, and we're going to write our answer in interval notation and in set notation. Well, the intervals of increase are indicated in red. I sort of trace them in. Now, what throws some people off is this arrow. They say to themselves, well, that arrow's pointing down. That means maybe it's an interval of decrease. That's wrong. We always read, when talking about intervals of increase or decrease, from left to right. So regardless of what the arrow on the curve is showing you, you read from left to right. So imagine that you're a little person standing on the curve and you take a step to the right. Will you go up or down? Well, if I'm right here, if I'm a little person at that part of the curve, if I take a step to the right, I'm definitely going up. That is an interval of increase. Even though the arrow that I showed earlier points down, don't pay attention to that. We're not looking at that arrow. We're going from left to right. Now, how do we state the interval of increase? Well, what we do is we can take those portions of the curve and we can then indicate where those portions relate on the x-axis. So those red portions of the curve relate to the parts of the x-axis that I've shaded in green. And now what we're going to do is we're going to state the intervals indicated in green in both set notation and in interval notation. So in set notation, I would say x can be any number less than or equal to 3. So in other words, or x can be any number greater than or equal to 1. So in other words, if you give me a number less than or equal to -3, I said 3 earlier, I meant -3. If you give me a number less than or equal to -3, and then you go to the point on the function corresponding to that x value, if you take a minuscule step to the right, you will go up. That's what we mean when we say an interval, an increasing interval. Similarly, if you give me a number greater than or equal to 1, and you go to the corresponding point on the curve, so say for instance you give me an x value of 2, if you take a minuscule step to the right, you will go up. If you give me a point, again, to the left of -3, suppose you give me the point -3, suppose you give me the point x equals -4, and you take a minuscule step to the right, you will go up. Intervals of increase. At this point, I'm just going to take a quick little moment and talk to you about the definition. There's a little bit of an argument as to whether we should include -3 or not include -3. Personally, I think we should include -3 because the definition of interval of increase that I know is this. If x1 is less than x2, then y1 is greater than y2. And so since that's the definition that I know, I think of -3 as being part of that drama. However, your textbook takes a different approach, and your textbook says that the definition of an interval of increase is if you move one step to the right, whether you go up or down. That's an easy way to visualize it, but it's not a technically true definition. So that's my little aside. For terms of you getting marks on a test, I will accept less than or equal to -3, and I also will accept less than -3. Or similarly, if we're using interval notation, I will accept a square bracket on the -3, or I will accept a round bracket on the -3. Similarly, on the interval on the right, I will accept you saying greater than or equal to 1, or I will accept you saying greater than 1, or I'll accept a square bracket on the 1 or a round bracket on the 1. I just ask that you be consistent in whichever way you choose to think of it, okay? Now, perhaps now's a good time for a quick refresher on interval notation. If we want to identify the interval between two values, we simply put those values in brackets. We use round brackets if the end values are not included in the interval, and we use square brackets if the end values are included. So if we're referring to the interval 3 less than x less than 5, we write 3 to 5. Both have round brackets. If we're referring to the interval 3 less than or equal to x less than 5, we write the interval this way. 3 to 5, square bracket on the 3 because it's included in the interval. Okay? And the other examples are shown below. But what if there's no left or right bound? So for example, what if we want to refer to the interval x less than 1? At that time, at that time, what we can do is we can think to the far left, we've got negative infinity way out there, and to the far right, we've got positive infinity way out there. And so if I wanted to refer to the values where x is less than 1, I could say the left bound is negative infinity and the right bound is 1. We always use round brackets to refer to negative infinity or infinity. We always put negative infinity on the far left and positive infinity on the far right. So x less than 1 would be negative infinity to 1. X less than x greater than 1 would be 1 to infinity. Okay? And finally, if we want to refer to all real numbers, we would say negative infinity to infinity. Remember, if you have a negative infinity, it belongs on the far left. If you have a positive infinity, it belongs on the far right. And in either case, you must use round brackets for those, for that part of the interval notation. Now, let's get back to the question. State the decreasing interval. Well, we can trace the decreasing portion of that curve. We can indicate on the x values of x that are in the decreasing region. So if we take that red part and we bring it to its corresponding portion on the x-axis, we've got values between negative 3 and positive 1. Well, we can state those values using set notation as negative 3 less than or equal to x less than or equal to 1, or this is my preference, or it would be acceptable in this case to write negative 3 less than x less than 1 because that's how your textbook thinks of it. Now, in interval notation, if we're saying negative 3 less than or equal to x less than or equal to 1, we say negative 3 to 1 and we use square brackets. But if we say negative 3 less than x less than 1, we use round brackets. Now, let's determine the intervals of increase or decrease in set notation and interval notation for the function shown on the right. Well, we see here that this whole part of the curve right here, that's all an interval of increase. It's an interval of increase because if I'm a little guy and I'm standing at some point on the part of the curve, if I take a minuscule step to the right, an infinitely small step, then I am going, an infinitesimally small step, I should say, sorry, I will go up. That makes it an interval of increase. And similarly here, this is also an interval of increase. If I take a minuscule step to the right, I will go up. Do not pay attention to that arrow right there, because that arrow is indicating movement to the left. It's important for the graphing of the curve, but it's not important for determining an interval of increase or decrease. Okay, so if we focus only on the left side, we see the entire left side's increasing. Therefore, every x value less than negative 1 corresponds to a point on an increasing interval. Similarly, if we focus only on the right side, we see that the entire right side is increasing. Therefore, every x value greater than negative 1 corresponds to a point on an increasing interval. We do not say that x equals negative 1 is part of an increasing interval, because at x equals negative 1, there's no point at all. And therefore, the increasing interval is the interval in which x is less than negative 1, coupled with the interval in which x is greater than negative 1. So if we're going to state it in set notation, we state it like this. And if we're going to state it so we stated it in set notation, we would do it like this. And if we stated it in interval notation, we would state it like this. Okay? Now, one thing I want to point out is whenever we use interval notation, these are always x coordinates or describing the behavior of the x coordinate. We do not put y coordinates in this interval notation. So I'll see people describe what's going on here. I'll see people describe it as negative infinity to positive infinity. Now what they're doing is when they say negative infinity, they're referring to this x coordinate, but when they say positive infinity, they're referring to this y coordinate. This is wrong. The way you describe that is negative infinity to negative 1. When we say negative infinity, we're describing this x coordinate, but when we say negative 1, we're describing this, when we say negative infinity, we're describing this x coordinate. And when we're describing when we say negative 1, we're describing this x coordinate. Those are x coordinates in there, not y coordinates. Okay? Now, in this case, let's graphically determine whether this curve is even or odd or neither. If the function's even, then reflecting it in the y-axis will make it fall back onto itself. Well, if I reflect the right portion in the y-axis, I get this. And if I reflect the left portion in the y-axis, I get this. That is definitely not the same curve. So that is definitely not an even function. Okay? The fact that the function is not even does not necessarily mean that the function is odd. We need to check that. So let's check whether it's odd. If we rotate the top half of the function 180 degrees around the origin, it lands exactly on the bottom half. Similarly, if we rotate the bottom half 180 degrees about the origin, it lands exactly on the top half. Therefore, the function is odd. Now, in this, and to show you what I mean, if we were to take this right portion and we were to rotate it 180 degrees, it would exactly fall onto the left portion. Similarly, if we took that left portion and rotated it 180 degrees, it would exactly fall onto that right portion. Now, let's look at this one. Let's determine whether this is even or odd or neither. Well, we can see the left side reflects exactly on the right side of the function if reflected in the x-axis. So for instance, look at this left side right here that I'm showing in red. If I reflect that in the y-axis, it lands exactly on the other side. And similarly, if I reflect the right side, it falls exactly on the left side. So the function is therefore even. Theoretically, it is possible for a function to be both even and odd, specifically if the function is just the x-axis. So that is possible. So I guess theoretically we could check. But if we were to rotate this function 180 degrees about the origin, it would end up looking like this. So we can say that the function is even, but the function is not odd. Now, let's look at the function shown here. We want to determine if this is even or odd or neither. Well, if we were to reflect it in the y-axis, it would, if we were to reflect it in the y-axis, it would look something like this. So that is definitely not an even function. And if it was to be rotated 180 degrees about the origin, it would look something like that. That's a little tougher to show. But that means it's definitely not an odd function either. So this function is neither even nor odd. Now let's algebraically determine whether this function is even or odd or neither. You might remember that a function is odd if f at negative x equals negative f at x. And a function is even if f at negative x equals f at x. Okay, that was our definition from a while ago. So, to determine whether a function is even or odd or neither, we need to determine an expression for f at negative x. If this expression is the same as f of x, then the function is even. If the expression is the same as negative f of x, then the function is odd. If neither is true, then the function is neither even nor odd. Now, recall from function notation that when we say f at x equals 5x cubed minus 7x, what we really mean is f at block equals 5 block cubed minus 7 block. Now, if I'm asking you about f at negative x, then I'm saying the block is negative x. And then I can simplify that expression. Now, negative x cubed is the same as negative x times negative x times negative x, which is negative x cubed. In other words, negative x quantity cubed, which is this one, is the same as negative x cubed. So I can plug in negative x cubed for negative x quantity cubed right here. I can also distribute this minus sign here. I can then simplify, and what I get is that f at negative x is equal to negative 5x cubed plus 7x. I want to simplify that expression. Well, f at negative x clearly does not equal f of x. So therefore, the function is not even. Now let's see if the function's odd. We figure out what is negative f of x. Well, negative f of x is negative quantity f of x, which is what we've written here. We then distribute that minus sign into the bracket, and we get negative 5x cubed plus 7x. And we see that f of negative x actually equals negative f of x. Therefore, the function's odd. Let's do another one. F of x equals negative 2x squared plus 7. To determine whether the function's even or odd or neither, we need to recall our function notation and determine an expression for f at negative x. Well, if f of x is negative 2x squared plus 7, then f of negative x is negative 2 times negative x quantity squared plus 7. Well, negative x quantity squared is negative x times negative x, which is x squared. So I can replace this negative x quantity squared with x squared. And when I do that, I get f of negative x equaling negative 2x squared plus 7 right here. F of negative x equals negative 2x squared plus 7. Well, that's exactly the same as the expression for f of x. So since f of negative x equals f of x, therefore the function's even. It is theoretically possible for a function to be both even and odd, so we can determine an expression for negative f of x and compare it to f of negative x. If we do that, we see negative f of x is 2x squared minus 7. It's not the same as f of x, so therefore the function's not odd. Therefore, the function is only even. And finally, we will look at this next question here. F of x equals 6x to the 5 plus 2x squared minus 9x. And let's see if it's even or odd or neither. To algebraically determine, we determine an expression for f of negative x and compare it to f of x and negative f of x. Well, f at negative x ultimately equals, after we simplify it, negative 6x to the 5 plus 2x squared plus 9x. Therefore, that does not equal f of x. The function is not even. Negative f of x is negative times quantity 6x to the 5 plus 2x squared minus 9x. And we get an expression that does not equal negative f of x. So we know that we've determined f of negative x already. F of negative x we saw on the last slide was negative 6x to the 5 plus 2x squared plus 9x. We saw that f of negative x was not the same as f of x, so therefore f of x is not even. And then we keep this expression for f of negative x that we've already found, and we're going to compare it to negative f of x now. Well, negative f of x is negative 6x to the 5 minus 2x squared plus 9x. That's not the same as negative f of x, which is in this circle. Since it's not the same, the function's not odd. So it's neither even nor odd. Now let's talk a little bit about end behaviors. Let's look at this function on the right. We have a horizontal asymptote to the left at y equals 0. As x goes to the extreme left, y goes to 0, and as x goes to the extreme right, y goes to positive infinity. Now, the y value never achieves 0 as we get to the far left. It's an asymptote. And the y value never achieves infinity as we go to the far right. And so, therefore, the y value of the curve never actually attains those values, but we still say that the end behavior is such that it's going towards those values. And so this is a description of limits. So as x goes to negative infinity, y gets closer and closer to 0. And as x goes to positive infinity, y goes closer and closer to infinity. We've just described the end behavior. How about this curve? Y equals cos x. We're familiar with this one. Well, the function y equals cos x varies between -1 and 1 in both directions. Therefore, there are no discernible end behaviors. How about this curve right here? We've got a horizontal asymptote to the right at y equals 2. And to the left, we've got we're going up towards positive infinity. So as x goes to the extreme left, y goes to positive infinity. And as x goes to the extreme right, y goes to 2. So we can write the end behaviors as that. As x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to 2. So 99 times out of 100, if you're asked for end behaviors, you're going to write this. As x goes to negative infinity, y goes to blank. As x goes to positive infinity, y goes to blank. And you're going to fill in the blanks.